the homework in this section is going to give you an equation or an inequality, or sometimes a pair of equations or inequalities, and ask you to describe the region that's described by that. So I want to just take a look at two examples. Some of the homework in this section will stretch you a little bit because even though we live in a three-dimensional world, doing math in a three-dimensional space is a little bit new. But I don't want to do too many examples and just give away all of the tricks. I want you to try the homework and struggle with it a little bit. And I'm more than happy to answer questions if you find that you struggle with some of them a lot. Okay. All right. So I want to just start with this region, okay, which would be the set of all points that satisfy this equation. Now, one thing you might notice is that the equation, and I should probably say describe the region in 3 space, okay? Because if there are only x's and y's, just by looking at the equation, I wouldn't know whether I'm working in 2 space, the xy plane, or in 3 space. Now I know, we're in 3 space, okay. Often, though, when my equation just involves 2 variables, I might choose to start by graphing in the plane determined by those variables. So, in the xy plane, I know that x squared plus y squared plus 1 is just the unit circle. Okay. So now, if I'm in 3 space, I'm definitely going to have that unit circle on the xy plane, but the equation doesn't put any constraints on what z can be. So basically, I can take that circle and I can translate it, or if you remember we had a fancy word, I can extrude that parallel to the z-axis. So I'm going to get a whole bunch of circles stacked on top of each other. I can just extrude this vertically. So I'm going to be getting a cylinder. So this would be a cylinder of radius 1 centered on the z-axis. And you'll notice that would be a surface because we're just talking about the points that are on that cylinder, not the points that are inside of that cylinder. So this would have surface area, would not have volume. Obviously, since it goes forever up and down, it has infinite surface area, but it has 0 volume. Okay. All right. Now, if you're asked to describe something, there are several ways to describe it. Here I've described it in words. Here I've described it by graphing it. Both of those are valid descriptions. If I want a particular type of description, I might be more specific. I might say graph this, or I might say describe it in words, or I might say do both. Okay. Here, I'm being a little bit open-ended, just describe it. Okay. All right. Now here I've got an inequality. In general, when you have an inequality, you want to first of all take a look at what the boundary is. The boundary, in this case surface, would be x squared plus y squared plus z squared equals 1. The boundary is always what you get if you have equality. That's true whether this is an inclusive or a strict inequality. The fact that this is inclusive just says that the boundary is going to be included. Now I recognize that that's actually the unit sphere. The unit sphere, should mention this, is the sphere of radius 1 centered at the origin. Just like the unit circle is the circle of radius 1 centered at the origin in 2 space. Okay. So that's my boundary surface. Now in 2 space, if I want the boundary to be included, I draw it with solid lines, and if I want it not to be included, I draw dashed lines. In 3 space, we're going to let that go. Because in 3 space, I'm already using dashed lines to indicate what's the back part of the surface that's behind other stuff that's in front of it. So here, I would just say in words that the surface is included, the boundary surface is included. Or if I've written the inequality, I can see that the boundary surface is included. Okay. But then that boundary divides 3 space into 2 parts. I've got all of the points that are inside the sphere. Now I can't touch those because I can't get through that boundary, but I've got all the points inside the sphere, and I've got all the points outside of the sphere. So when I've got an inequality, I want to shade the appropriate side of the boundary. So the question is, do I want the points inside or outside? Well, if I recognize that this is just the square of the distance to the origin, and I want it to be smaller than or equal to 1, I want the points that are closer to the origin. That's going to be the points that are on the inside. Sometimes you can sort of recognize what side you're going to shade. Other times what you might want to do is just pick a test point. Pretty obviously the origin is on the inside of the sphere. If I plug in 0 for x, y, and z, that makes the inequality true. That tells me the origin is on the side of the boundary that I want to shade. So this would be, I'm going to actually shade using a different color so that I don't lose track of the boundary. This would be the solid unit sphere, or I could refer to that as the unit ball. A solid sphere is also called a ball. If you just say sphere, in general it means that you're talking about the surface of the sphere. Okay, that finishes up section 13.1 for us. So we've made it through our first section in multivariable calculus.